In this video, we'll be animating the spherical pendulum, which is the three-dimensional pendulum, and we derived the equations of motion for this in a previous video. A link to that appears above, and I'll also put a link below in the description to the video. But these are the equations of motion we derived in terms of angles theta and phi. And just to remind you, theta is the angle you associate with a typical pendulum between the pendulum and the vertical. And phi is this angle here that it makes above the vertical axis. Okay, the y-axis which points straight upwards, phi is a rotation about that axis. So what we need to do first is we need to solve the equations of motion, and in order to do that, the first step is to rewrite the equations of motion in state space form. To do that, we take our two equations of motion. Let's number them number 1 and number 2. And we've got to rewrite them in terms of the accelerations. So the first equation becomes theta double dot is equal to, and we just take the terms to the other side and flip the signs. And we do the same thing with phi double dot. And those are the equations of motion just rewritten. And now to write it in state space form, we come up with a state space vector, a state vector that looks like theta dot, theta and phi. And we can just plug this in with the velocities, the lower two elements. And that is just the same equation written in state space form. And we could rewrite that in general as y dot is equal to some function g, where g is equal to this vector on the right. Okay, that's going to become important later when we implement this. So now in order to get this into a form that's suitable for a computer, we discretize it and we say that y dot is the difference between y at time t plus 1 and at time t divided by delta t, and that is equal to g. And then, of course, rewriting this, we can get it in explicit form that y at time t plus 1 is just y at time t plus delta t times g. Let's put a box around that. So what we're going to do in the next part of the video is I'm going to refactor some code that I wrote previously. And the idea is that we need to replace this function g with the appropriate model for this problem. Okay, and then probably something I just want to say, let me do it here in blue. But if we look at the second equation, one of you might be in the question, doesn't cotangent blow up when theta is equal to 0? Because cotangent is just cosine divided by sine, and sine goes to 0 when theta goes to 0. So what happens when the angle goes to 0? And what you're going to find interestingly is that it never gets to 0. When there's actually some angular momentum, angular rotation, phi dot, some angular velocity around the vertical axis, theta never gets to 0. And the way we can see that is if we look at this equation, really where that equation came from was the second of the Lagrange equations, and it in fact looked like d by dt of ml squared times phi dot times sine squared of theta equals 0. When I took the derivative of this, I ended up with this equation. But if we take a step back, what this is saying is really the angular momentum, the change in angular momentum is 0. So this term, which is the angular momentum about the vertical axis, there's conservation of that. So I could say that that is equal to a constant. First of all, let me cancel the ml squared, but I can say that phi dot times sine squared of theta, sine squared of theta, is equal to, let's just call it L. But since that L is a constant, therefore initially, whatever phi dot is initially, and if we use sine squared theta initial, that is equal to some initial, I'm going to call it angular momentum, but it's angular momentum actually without the ml squared. But angular momentum is conserved. So what happens is if this is always constant, okay, this quantity must, let me just rewrite it. in a different form. This can be rewritten as, therefore, theta dot is equal to, I'll do it in terms of L naught, some initial constant divided by sine squared of theta. And I guess the point I'm trying to make here is, in order for this to be conserved, this L initial, L naught, as sine squared theta goes to 0, so what happens is the angular velocity phi dot becomes infinite. So in other words, as the pendulum falls towards theta equals 0, if it's got any angular momentum about the vertical axis, it will speed up as to throw the mass back out. So in fact, you will never see the angle of 0. In fact, you never see a negative angle in the case of a spherical pendulum. So that's to be expected, but I thought it would be useful to point that out. And I guess the last thing I want to say is we're going to need the kinematics from the slide before. And let me delete this and put it in here, I think, just so we can have it all in one place. But I want you to see this, and now that you've seen it, I'm going to delete it, because what we're going to need for our animation is the kinematics. Whoops, I don't want the numbers. And let me just copy and paste that onto the other slide. There we go. All right, now we have all the ingredients that we need to do this animation. And I think just for completeness, let's just add some numbers here. We will call this equation 3, and we will call this equation 4, and we can call this equation 5, and we'll call all of these equation 6. Oops. Equation 6. In order to animate the spherical pendulum, I'm going to borrow the code that we produced in the double pendulum animation. Here is that video. A link appears to it above. And also, I'll put a link in the description below the video. But if I click on this link, this takes us to the GitHub repository. And all I want to do is take this raw code, copy it, and paste it into a new document. I'm then going to save this new document as, we'll call it spherical pendulum.py, and I'm going to save it in a new environment where I've installed NumPy and Pygame and Matplotlib. All right, so the first thing I have to do is I need to rewrite this G function based on what we did on the previous slide. So really, I'm applying equation 3 and equation 4, I guess. So I've got to create this vector where I've got the accelerations in the top 2 elements and the velocities in the bottom 2. And let's see the best way to do it. I've installed a package, by the way, called Greek letters, which allows me to use Greek symbols as my variables. Very useful. So I'm going to do that here. The first thing we need to do is we need to pick off the velocities and the positions, the angles from the state vector. So I'm going to call that theta dot, phi dot, let me get this right, and then theta and then phi, and that is equal to what we had before. Let's write it like this. Sorry, it's a little bit messy. Okay, I can take out the rest of this because I'm going to rewrite that function. But from the state vector, I get phi dots, and I get, let me put this all in one line. I think it looks easier to read. Okay. So the next thing that I want to do is I need to put the expressions for the accelerations. And in fact, to save time, I'm just going to paste them in here. And again, this is just off the previous slide. The only point I want to mention is, since this math package doesn't have the cotangent function, instead of multiplying by cotangent, I'm going to divide by tangent. And in order to use it, I need to import it here. And then this is the same. The RK step is the same. The variables, we don't have 2 masses and 2 lengths, of course. We now just have 1 of each. So we have a mass variable and a length variable, and I'm just arbitrarily going to make this 2 kilograms and the length 1 meter. And let's look down here, y1, y2. So y2, which is actually y position 3, but this, what I'm calling here y2, is actually phi, And I don't think we need to plot that initially. Let's just fix this up, and we can fix the legend. This is just going to be theta instead of angle 1. And angle 2 will now be phi. I realize I haven't returned my matrix here. So let me add the return. NumPy array. I just put the expressions in. And this will be theta double dot. Phi double dot. Theta dot. And phi dot. And I've got to put square brackets around that. Okay, this is my vector G that we defined on the previous slide. That's exactly it. Okay, it's got the accelerations in the top 2 elements and the velocities in the bottom 2. And now I'm ready to run this. Invalid. Oh, I see what's happened. It's because my starting point is that theta was equal to 0, and I've explained to you theta can't be equal to 0. When theta is 0, tangent is 0, and this whole thing blows up. So let's just treat this as a simple pendulum for now, and we won't have any phi or phi dot. We'll just let theta equal 1 radian, and we'll let it go from there. And there we go. It's oscillating between -1 and +1, much as we would expect. Now let's make phi dot non-zero. Let's make that 1 as well. Run it again. And lo and behold, we now see that this pendulum is oscillating between 1 and between about 0.25. It doesn't, in fact, get to 0. I explained this on the previous slide. The reason it doesn't is, as it gets to 0, as it gets close to 0, the angular velocity, phi dot, increases, and it throws the mass out. So the angle theta is never 0, and it's, in fact, never negative either. Can run this again, and let's plot y2 at the same time now. And instead of running it for 10 seconds, let's just run it for 5 seconds. But just remember that y2, which is phi, will continually increase. And there you kind of see it. So you see that what happens is every time that this pendulum, I'm looking at the blue line, every time that theta gets close to 0, suddenly there's a very quick change in phi. It rotates very quickly and throws it out. Okay, we now have the results, and all we need to do is now modify the animation to make this work. I'm going to borrow a piece of code from before when we animated the double pendulum. Here is that code, and if I scroll down to the details, I can get the GitHub link, and I just want the raw version of this. Copy it and paste it into a new document. I'm going to save this, and I'm going to call it spherical pendulum.py. And the first thing that I need to do is I need to take my function g and replace it. This is the model that we now want for the spherical pendulum. Just going to paste that over there. The RK step is identical, nothing changes there. In the case of the update, this is going to change. First of all, I don't like scale there. I'm going to make this a global variable. I don't really like it there either, but it's better there. And update now. So let's just go back to the loop and remind ourselves what's happening. While true, this just runs indefinitely. We're looking for a key press here to quit. The first thing we do is we update, based on the state vector, we update the location on the screen of the mass of the pendulum. And then what we do is we render it. So we update, we render, and then we increment time and we take our Runge-Kutta step, okay? So we've got to update and then we've got to render. And by updating, we're passing the variables theta and phi. That's what are in the 2 and 3 position. So instead of A1 and A2, I can call these theta and phi. And then what we're now going to calculate is x, y, and z. By the way, guys, I use z and z interchangeably. First half of my life it was z, and then it became z, and please don't be confused by this. Z and z are the same things. So what we're doing now to calculate x, y, and z, this is just the kinematics that came from the original setup of the problem. Let me put back that original slide. There it is. And we're talking about equation 6. So I'm just implementing equation 6. The only point I want to make is there's a change of coordinates, okay? In the case of the model, the y-axis was positive upwards. In the case of plotting to the screen, the y-axis is positive downwards. So there's a sign change. There's also going to be a sign change on the z-axis in order to keep it as a right-handed coordinate. This will be L times sine of theta times cosine of phi. All right, this was L times cosine of theta. And this was L times sine of theta times sine of phi. And what I want to do is scale this length by 100. This was the scale that I put in here. And why am I doing that? Because L is the length for the structural model, and I want to scale that into pixels for plotting. So I'm just going to multiply this by scale, the length here. And I'll do the same thing here, and I'll do the same thing here. And remember that I need to add my offset for the x and the y coordinate. Okay, and then instead of returning the 2 points, I'm only going to be returning 1 point, which is just x, y, z. That's it. Okay, and what I want to do is actually convert these to integers. Because for the purpose of plotting in Pygame, everything needs to be an integer. So I'm returning a tuple containing these 3 components of the point, x, y, and z. All right, very good. The render function, we'll touch that in a second. I'll come back to render. What I want to do here is, let's make the screen a little bit bigger, 1024 by 768. And what I did with the offsets, this was supposed to be the middle of the screen. So this would just be width divided by 2. I'm going to floor divide to make sure it's an integer. And this would be height, maybe divided by 4. Okay, fine. The parameters, this is just M and L. And this goes away too. We don't need A1 and A2. So we've got M equals and L equals. And I mean, this is somewhat arbitrary. I'm just going to make mass 3 kilograms and the length 4.5 meters. Gravity, as always, 9.81 in SI units. As a starting point, let's just test the simple pendulum again. We'll make that 1. And what goes on here? So in the loop now, the update function is only returning 1 point, not 0.1 and 0.2. So I can just call that point. I'm then going to feed that point into the render routine, for plotting. All right, so the render routine is going to take this point, which is the point that the pendulum is at. It's an x, y, z coordinate. All right, let's see how that works. Let's make some space here. So the first thing I want to do is to say that x, y, and z are points 0, 0.1, and 0.2. That's not point, that's point. All right, so I've just picked off x, y, and z. And then this can go away. I'm going to say if previous points. So this is where we did the trace. Let's not deal with that initially, the trace. And then when I merge the trace with the screen, let's just comment that out initially. In terms of the pendulum, we don't have 2 pendulums now. We only have 1, so I can get rid of 1 of them. This little circle is, it's just for effect at the top of the screen. That does nothing. We'll get rid of this. Okay, so the line is still going from the offset, but now it's going to x1, y1. And the circle is at x and y. And I'm just going to arbitrarily set the size now to 40 pixels in radius, the size of the pendulum bob. And then it's returning x and y, not x2 and y2. I think that is it. All right, so let's try to run this. In this case, it's not S Pen, it's Spherical pendulum, I called it. Offset. Oh, that's a typo. Offset. Positional argument 0.2 in render. Oh, here, render is only getting 1 point. I needed to fix that. All right. Oh, we didn't import tan at the top. There we go. Very good. Looks like a simple pendulum. All right, let's see what happens when phi dot now is non-zero. So let's go back to our initial state and let's make this 1. So phi dot is 1 radian per second, and let's run that. Yeah, so it looks... You know what I think we should do is scale the size of the pendulum bob so that as the z direction, as it moves away from us, it gets smaller, and towards us it gets bigger. We'll use the z coordinate as a way to scale the bob. So let's go, we'll do that in the render routine, and we'll do it right here. We'll call it a z scale. And z, we want it to go from -1 to 1, so we need to normalize it by dividing it by L. Well, it's not L because we've scaled L, so it should actually be scale times L. Remember, we've multiplied L by 100, so z is actually a lot bigger. So that will make z between -1 and +1. We want to add 2 and subtract 2 minus. That would be the way to do it. Okay, very good. And then, so now that would now be a scale from 1 to 3. If I multiply it by 10, it would be from 10 to 30. And 10 to 30 seems to be a good size for the pendulum bob times the mass. Okay, so now I'm going to take that z scale and the size of the pendulum bob here. I'm going to make it mass times the z scale. And in fact, I need to make that an integer. Let's see how that works now. Negative radius. Oh, this needs parentheses around it. That actually looks pretty good. All right, can we get the tracing in here now? In order to draw the tracing, we want to go from, in fact, I don't need this. I can just call this previous point here. From previous point to xy. All right, and then we'll blitz it. You know what, let me do the weight on the string and the line as well. I think that would be pretty neat. So we could, instead of having the weight here, we'd base this on the z scale as well, and let's just multiply it by 20%, I'd say. We'll do the same thing here for the thickness of the string. Maybe make that a little bit thicker. So now the thickness of the string and actually the trace of the curve will be thicker or thinner depending on whether it's in the foreground or the background. I like the look of that. Let's run that. Got to float. Oh. I've got to put the int around all of that. There we go. That should be it now. I think that actually looks really good. So I think maybe one last thing I'd like to do is just turn this tracing on and off. Maybe even clear it. So the way I'm going to do that here is just in our game loop. I'm going to look here for a key press. And what we need to do is say if event type is equal to key down. If that happens, if there's a key down event type, then we can look for specific key presses, what key was pressed. So we would say if event key, whoops, not key down, but a key is equal to, let's just say the T key. T for trace. So K for key, subscript T. So what do I want to do if the T key, I want it to stop tracing. And it's doing the tracing here by blitzing the trace layer with this. Here's how I'm going to do that. I'm going to put a flag here called isTracing. We're going to set it to true. And then up here, we will only say if is tracing. So only if is tracing is true should you draw the trace layer. And then all that happens if you hit this key is it will say that is tracing is equal to, you just want to flip the Boolean value, so just not is tracing. Whatever it was before, we just want to not that. And while I'm at it, let's also allow us to clear this. So if event.key is equal to, let's say, lowercase c, c for clear, then what we want to do is we just want to white out, we want to clear the trace layer, right? So this trace layer here, we just want to fill that with white. So that's easy enough. So we just say trace fill with white. And that should be it. Let's try to run it one more time. Okay, so if I hit the T key, T toggles that trace layer on and off. Perfect. And if I hit the C key, it clears the trace layer. Cool. Okay, so let's look at a few different examples. I don't know what happens if we make this 2 and 1, for example. Speed it up a little bit, phi dot. Well, that's kind of interesting. It's theta is pretty much stationary. You would expect that as this thing sped up more, right, it would fly out at right angles. Let's see what happens if I do that. If I speed it up from 2 to, say, 7 radians per second, which is very quick. Interesting. Seems to stabilize the pendulum when it spins very fast like that. It's almost like a gyroscope. Let's pull it down to something a little more reasonable and set it on its way. And there you have it, the animation of the spherical pendulum. I think that's all I want to do for this video, so I'm going to cut it at this point. I hope you found something useful in it. If you have, please go ahead and hit those like buttons so that others can get to view it. Or better still, subscribe to the channel and smash those bells so that you can get notified of new videos as they're released. If you have any questions or comments, I'd love to hear from you in the comment section below. Thank you for watching this video, and I'll catch up with you in the next one.